What is up, most distinguished patrons of this channel? Today we are going to be diving into the world of TIG welding defects or weld defects with the TIG process. And I am going to cover a ton of common ones that you're probably well aware of, especially if you're new at TIG welding. And I'm going to cover some you probably never heard of or are unaware of that could make a difference, especially on things other than mild steel. So with that said, let's get into it. So one of the interesting things with TIG welding is that it also has all of the same defects as conventional, say, MIG and stick welding, but it also has some that are unique to it. And the overall defect situation with TIG is interesting in itself because the defects are often very minor or minute if you're decent at TIG welding, and even if you're bad at it, the defects aren't typically as bad as what you find with MIG or stick. And I got this here. I don't know where this came from or who was practicing on it, but this is pretty atrocious. Came out of a scrap bin. And I was looking here, and like this, which is appears to be all stick welds, like there's porosity, cold beads, like it's pretty evident when you look at this that there's a lot of defects here, right? Well, with TIG welding, typically you're not going to see welds this bad, and the defects tend to be so minor sometimes that people either overlook it, don't care about it, don't understand it, and that's why I think that it's worth doing a whole video just on this topic. That way you guys can look at your welds or other TIG welds and understand a little bit more about what's going on. And one of the things I'm going to cover as well in this video is kind of a thought process of at what point are defects with TIG a concern, because I understand like the real world dictates that not all welds can be perfect. There simply isn't enough time in a day, and oftentimes people don't have high enough skill level to achieve perfection or near that. So at what point do you really need to concern yourself with fixing a defect? So on this list that I made, we have the most common TIG welding defects as well as some that are fairly less common that you may be unaware of, but we're going to start out with some easy ones first. First one being undercut. Now, undercut can exist on TIG welds just like it can on stick and MIG. However, undercut with TIG tends to be very minimal. And what I mean by that is, well, you're depositing smaller welds in both MIG and TIG, so any undercut you might have, unless you really don't know what you're doing, tends to be very minimal and minor. Now, in the perfect world, you don't want any undercut on your weld because you're more or less thinning the base material and giving a point for a crack to propagate from. So that's generally speaking undesirable. Now with TIG, it's really easy to go back and fix undercut. You can just start at the start of the undercut and then do another bead over it, and it's fairly easy. With stick and MIG, it tends to be a lot harder to fix undercut simply because you have to deposit a lot bigger weld, and you kind of wind up in a situation where you might have 2-3 extra passes just trying to clean up undercut that you don't really need, and that's undesirable. But undercut will happen a lot when you're practicing TIG welding. Now, if you're just doing beads on plate, you might not see too much, but on fillet welds, that's going to be a very common thing to happen. Now, when you're welding things like tool steels, chromoly, and all sorts of other like non-mild steels, forgings especially, you're going to find that undercut is far more prevalent on things other than mild steel with TIG, and there's ways around it. And in this video, I'm not going to be covering like how to weld those types of steels without undercut, but I just want to make you aware that the type of material you're welding on definitely plays a huge role into how easy it is to undercut it. The thickness of the material that you weld also plays a role. If you attempt to weld very thin to very thick material, that will also produce a fair amount of undercut if you're not careful. The easiest ways to fix undercut with TIG is simply to hold a tighter arc, to use less amperage. You guys got to remember that as you increase amperage with TIG, your arc cone gets wider and thus your molten puddle gets wider. So if you use excessively high amperage for what you're trying to weld, you're going to end up basically cutting back at the material higher and lower than the joint that you're trying to fuse. And if you don't push enough filler, you will leave that scoop out of that material. And that, speaking of filler, is another way to solve undercut. If you're not pushing enough filler as you're welding, you will produce undercut. Like basically a fusion weld with TIG where you're not adding filler is 100% undercut. That's what you're doing. Well, if you don't push enough filler as you're making a weld, you will leave that left behind. And again, it's undesirable simply because your base material is now thinner or has a place for cracks to propagate at. You don't want either of those. Now, lack of fusion, this one probably will confuse some of you, and that is because TIG welding is universally known as a process that can achieve 100% root fusion all of the time, and is generally not an issue with the process to achieve fusion, aka you don't have a cold bead that just bridges two pieces of metal. Now the interesting thing is that with TIG welding, if you do not run enough amperage, it too can suffer a lack of fusion, just like MIG, just like stick. So it is imperative that you use appropriate levels of heat input for what you're welding. Now, if you're welding sheet metal thicknesses, you're not going to get a lack of fusion or a lack of root penetration or root fusion. It just isn't going to happen. However, if you're welding thicker steel, like say 3/16 or maybe 1/2 inch, 3/8, anywhere in that ballpark, somewhere between, I don't know, 4 and 5, 6, 7, 8 mil or bigger, you can get a lack of fusion. And that is, with TIG, almost universally caused by two things. One, not enough amperage, and two, you're pushing too much filler in too fast or lay wiring it. If you just take the arc and run it over the filler wire rather than, say, pulling it out and pushing it back into the puddle, you will likely create a lack of fusion, especially, again, if you're not running enough amperage. So to fix a lack of fusion, you need to run appropriate amperage, aka hot enough to where things melt. You need to keep a tight arc. If you're long arcing it, it will spread the puddle out, and that will not drive the heat into a small area. So keep the arc tight. Don't try and run high amperage and move fast either. If you're trying to make TIG into like a spray arc process, you're fooling yourself. You will make a decent looking bead, but more than likely the faster you go, the less fusion that you will have. You need to take an appropriate amperage for the thickness of the material and then move at an appropriate speed. As far as what that speed is, well, guess what? If you're going to weld 1/4 inch or some thicker steel, maybe you should do a test joint the way that you think is correct with your TIG welder, and then cut and etch it and look at what the penetration is. If you have a lack of penetration or a lack of fusion, then guess what? You need to change something. More than likely tighter arc, slower travel speed, etc. You get the picture. Now, another very common defect with TIG, this is probably very prevalent in new people who are just learning TIG, is a concave bead. A concave bead is undesirable because it lacks throat depth. You may have a weld that appears to be properly sized for the thickness of material you're welding, but the concave nature of it basically produces a very thin throat depth, therefore not enough reinforcement, therefore you will have a weak weld, not enough material. Now, TIG in particular is really bad with concave beads simply because of the way it works. If you don't push enough filler, the TIG process is happy basically just to produce a undercut fusion weld instead of an actual reinforced weld. And it's so easy, like stick and TIG, because they deposit metal as part of the arc that's ongoing as you're welding, you simply can't produce concave beads the same way like you can with TIG. To fix concave beads is really simple. You need to push more filler, use a bigger diameter filler, use less amperage, hold a tighter arc so you're not melting so much material off. Like the leeway you have for amperage on TIG on anything thicker than maybe 3.2 mil 1/8 inch material, you can run anywhere between 100 and 200 amps on that material and still make a acceptable weld. It all comes down to holding that tight arc and pushing enough filler. So again, if you're seeing a lot of concavity to your welds, recognize it, understand that it's a defect, and then push more filler, slow down, do something to get more reinforcement on that. Now, another discontinuity that's of concern would be porosity. Welding porosity is very common with the stick process, less common with the MIG process. If your shielding gas has issues, that's normally where you would see it, or you have like material contamination. Well, porosity with TIG generally comes down to two reasons. One, surface contamination, and two, lack of shielding gas. If you try and weld on oily or filthy or mill scale material with TIG, you will likely see porosity. And what porosity generally is little empty holes or voids, pores, that are in the finished weld, and you can sometimes produce it in the base material and trap it in there as your weld solidifies. And to fix porosity with TIG, the first thing you should concern yourself with is the base material clean enough to TIG weld. You need that stuff bright, shiny, wiped down with acetone if it's a critical TIG weld, so that it is clean and free of oil and any contaminants. If you have porosity issues still and your base material is clean, then you need to start looking at your argon. Do you have enough argon flow? Do you have a leak somewhere in your TIG hose? Are you running a big enough cup based on amperage? Those are all things that can contribute to porosity. Now, if you're welding on some old casting, especially aluminum, porosity is going to be part of life. You just have to deal with it, and you weld it. You get your porosity, you grind it all the way down, you re-weld over it, you grind the porosity out, and you keep doing that until you have solid metal. Like certain materials with TIG, you can't just consume that porosity and make it disappear. It just doesn't work. So it generally, if it's bad enough, you're going to have to do a lot of grinding. Like I know a lot of you guys don't want to grind a lot. That's why you're TIG welding. But guess what? Certain materials, you have no choice. Now, a good indication if you have a gas issue and that's contributing is look at your tungsten. If that thing looks like it has red powder on it or some kind of weird colors to the tungsten and you have porosity on your piece, more than likely you have an issue with not enough shielding gas, you got a leak or something. So always pay attention to that. And if you ever try and weld on galvanized, you can forget about it with TIG. You got to grind all that stuff off. You're never going to be able to get any decent welds. It'll be porosity city. Now this one I included because this is a fairly common thing, especially for new welders, but I also got asked about what the problem is with a tungsten inclusion. And what this is where you dip your tungsten into that molten puddle, which immediately kills the arc. And then to get the tungsten unstuck, you basically snap it and break it. And then you just start up with hopefully a new tungsten and just keep welding. Well, little do you know, maybe you don't know, when you do that, the tip of that tungsten gets broken off into that molten metal that is solidified and it stays in there. Now, tungsten melts at a much higher temperature than the weld. So even if you try and weld over it, that piece is going to be solid and it is not going to be diluted into the base material. And essentially what you have is kind of like a form of porosity. You have an inclusion that is not going anywhere. It can't be welded out. The only way to remove it would be to grind it clean and then weld over clean material. Now, is this a significant concern? If you're building yard art, absolutely not. It really isn't going to make any difference. If you're building 2000 PSI piping in a power plant, absolutely it could be. The inclusion, much like a pore, is a weak spot, and you could have a failure. A crack could propagate from there, and that is undesirable to leave in there. So in the case of high liability stuff that's x-rayed with TIG welding, they will go and x-ray that pipe, and an inclusion will show up as a higher density spot. And it's going to look different on an x-ray than porosity, simply because porosity would be like a void, so less density. Well, tungsten inclusion will show up as a pin dot of higher density, and guess what? High liability work means somebody's got to grind all the way to it, remove it, and then weld out all the way clean to get rid of that. So is this really a major concern? Again, if you're building something with liability, anytime you have this issue go on, grind it out and then weld over it. It's important to have attention to detail with things and don't get in bad habits, because you'll do them when you don't need to and you will have problems. Now, as far as like the tungsten getting swiped in the molten material where it doesn't kill the arc, is that going to leave an inclusion? Possibly. So in the pipe welding world, which I'm now involved in, we typically use 1/8" tungstens. One of the reasons is that the point tends to be a little bit stronger than 332, and if you're running it through the molten puddle by accident just a little bit, but the arc stays lit, aka the arc does not extinguish, odds are you are not going to leave an inclusion with that 1/8" tungsten. If you're using 1/16 tungsten or 332 tungsten, that thinner stuff, and the arc almost cuts out, it's possible that you would have contaminated something in that weld with it. Again, you know, the higher the skill you have, the less likely you're going to have an issue with this. But my opinion is, if you think there could be a piece of tungsten in your weld and it's a critical weld or something that needs no defects, grind it out. Here's something that a lot of people probably don't think of, and that is an undersized weld. TIG welding produces very small, thin welds. Like if you're trying to put down, you know, spray arc worth of welds in one pass with TIG, you're in the wrong process. And it's very easy, say if you're welding like, I don't know, 6 to 10 mil steel, so somewhere around 1/4 to 3/8 material, to put a undersized weld. Now, TIG welding is very strong. The welds are very strong, and they can achieve high levels of fusion despite not putting down much metal. And that's where the strength is that technically for the size, well, I'll put it to you this way. Stick and MIG cannot produce as small a welds as TIG that have any fusion on thicker material. And that's just the nature of TIG, because it's a high fusion process and you control the filler. You can achieve welds that no other process other than maybe laser or electron beam or something can produce. But anyways, back to what I was saying, undersizing your weld. A proper stick or MIG weld on 3/8 material might be a 3/8 throat depth weld, so pretty substantial weld. You do not want to get in the habit of putting, say, 1/4 inch size welds on 3/8 material and saying it's good enough because it's TIG. You're going to be mistaken depending on what you're building. Now, of course, if you're doing something for a company and they specify weld sizes and they're saying small welds are acceptable, do that. I'm not telling you not to. I'm just saying don't get in the habit of putting real small single pass welds on stuff and thinking that you're just fine, because you'd be surprised at what might happen if that part gets stressed. The easiest way to fix this is simply running more passes. If the weld is undersized by the look of it, put another 1-2 passes, put a weave pass on it, do something. Don't be shy. Now here's something that you guys are probably not aware of, and if you are, congratulations, you passed the test. But no, anyways, suck back. This is similar to undercut. Undercut would be like on a fillet weld on the side you're welding, it will be cut into or scooped out of the material. Suck back is somewhat unique with TIG. It can happen with other processes, but it's more common with TIG. And what that is say you run a fillet weld and you're welding really thin material to really thick material. The back side of the thin material will pull back towards the face of the weld and create more or less a form of undercut on the back side of the material. This is undesirable for the same reason why undercutting is undesirable, and that is you will have a very thin line where the base material is more or less neck down, and it will propagate a crack or just be weak simply because it's thin at that point. Probably the most relatable situation that this could cause you a nightmare of a bad day would be if you're building headers for your race car, your truck or something, and you're welding the tube to the flange that bolts to the exhaust manifold part of the cylinder head. Anyways, you have a situation where you have thin tube welding to thicker material, that's the flange, and what will very commonly happen is you will undercut or you will suck back the whole inside of the tube towards that flange, because again, you're TIG welding thick to thin. And that is why a lot of header manufacturers do not TIG weld the outside of the tube to the flange because of suckback concerns. Because that suckback or that internal undercut, when you expose it to high vibration and heat cycles, it will crack there 100%. And I've done repairs on headers where the whole tube all the way around it of well-known brand name headers out there cracked, and the people believe that's from vibration or something they did wrong, but they don't realize, you know, especially with stainless, that is a critical mistake. So if you're welding headers or something like that, or anything thick to thin, be very mindful of suckback, because in high vibration, temperature swings, whatever, you're going to have failure due to it. Another very common situation you're going to find suckback in is aluminum spool gun welding. Aluminum MIG welds, to get any kind of fusion, you got to run it pretty hot, and the process runs in the spray arc mode of transfer, which is hot enough already. And unfortunately, when you're welding thin material with the MIG process with a spool gun, you're going to get typically a lot of suckback if you're not careful, because that big bead will pull, and it's going to pull something out of that base material, and you're going to get that undercut, that suckback on the backside. So pay attention to that. To fix it, running more appropriate settings, doing different styles of welds. Like I said, on a header, welding the inner part of the tube to the flange, not the outside of the flange to the tube. There's all sorts of things you can do, and beyond a certain point, it might be unavoidable. Like if you're trying to weld 1/2-inch thick steel to 22 gauge metal, unless you have a laser, you're just going to have to deal with the probability of having some of that. Now here's a welding issue that is predominant mostly with TIG and maybe with laser welding processes, and that is base metal dilution or base material dilution. And what this is because the TIG process can weld without adding filler, whereas you have the MIG and stick processes, you are always adding filler while you're welding, because the arc is more or less melting your filler. The filler serves as both filler and as the electrode. Well, with TIG, if you do not push enough filler, or you just fusion weld, aka you're no filler at all, and you're just welding your base material together, you can have what's called base metal dilution. Now with normal mild steel, it's not really too big of a concern because the weldability of mild steel is really good. Now you're still going to have potentially your concave bead, your lack of throat depth, but it's not a serious concern from a structural standpoint. Now, where this becomes a serious concern is with certain alloys. Like if you go and TIG weld chromoly tubing or steel like AR500 or any number of tool steels, or even aluminum for that matter, or another good one would be cast iron or spring steel like a leaf spring. If you just try and fusion weld those, or you don't use enough filler, you will produce an extremely brittle weld due to partially carbon absorption. It will absorb carbon from that material and then become brittle, but there's a lot of other things at play with other tool steels besides just carbon. And long story short, your weld is going to be junk. So even if you go and do like a crappy root with not enough, reinforcement on those, and then you go back over and re-weld it, the root pass is probably highly suspect. So you always want to push enough filler material to the weld to where you are mixing an alloy. You have an alloy of basically your base material and the filler rod. You don't want on any kind of material realistically other than mild steel to just have the base material melting and trying to use that as filler. The only exception to that, and well, there's probably tons of exceptions, but in some cases that may be acceptable, like on say chromoly, if the part is being heat treated after it's welded. Since I don't think you have a heat treat oven, nor are you probably heat treating anything after you're welding it, avoid doing it, push enough filler, always have enough dilution of that base material with filler, and you're not just diluting the base material only. That's bad. Now, excessive heat input. Excessive heat input is somewhat unique in the way that it affects TIG welding, When you put, say, a stick rod at 200 amps that's supposed to run at 90 amps, it's not going to run very well and you're going to have undercut and all sorts of problems, right? Same thing with MIG. If you're running settings for welding half-inch plate on 1/8 inch, you're just going to blow holes and have problems. Well, with TIG, it's very common, especially for beginners, to be too slow on your travel speed, so you're just pumping massive amounts of heat, and also trying to weave too wide where you're just putting, again, massive amounts of heat. With the TIG process, you need to think and train your brain. Tell your dome that you need to move slow, consistent, and that you are not depositing a lot of metal. If you get that into your head, TIG will treat you very good. If you keep going back and trying to do, 70-18 size welds with TIG, you're going to have all sorts of issues with excessive heat input. Now, excessive heat input causes a lot of problems. One is you're going to have a lot of warping. You're going to probably have more issues with undercut. The grain structure of the solidified weld itself will often be subpar, as if by you're cooking the weld, not just on stainless. A lot of people think that cooking welds is only an issue with stainless. No, it's also an issue with steel. And that's why I'm a proponent against fusion welding over a weld. Say you put down a TIG weld and you don't like the look of it, and you just go back and just increase the amperage or weave or do something and just re-weld over the top of it. It's generally not a good idea to do that, because the grain structure of the solidified weld, if you do that immediately after you just did a pass and you don't let it cool, that grain structure of that weld will be compromised, and it will likely be weaker than if you had just let it cool and then welded over it with a little bit of filler. So be very mindful of excessive heat input. Now, on mild steel, this is mainly an issue of poor grain structure. When you get into things like stainless, you will basically eliminate its ability to be corrosion resistant by cooking the chromium or creating oxides on the surface. So you want to be careful of that with other things too. So again, just use appropriate heat input. Now, going back to fusion welding, where you're not using any filler, you're just fusing the material with the material itself, that is very common on things like thin stainless. Like, I'm certified to TIG weld basically unlimited fusion weld for pipe, okay? So just no filler, very thin, Schedule 10 or thinner pipe. And we in the piping industry do not use filler for stuff that thin in most cases. Now, that can work. However, you want to be very careful of fusion welding things. It goes back to the reasons that I mentioned in a base metal dilution, but also if you don't have like an argon purge on the back side of something, like say you're welding stainless headers and you're going to fusion weld them, right? What will happen if you don't have an internal purge on that tube and you just basically lace a bead right over the top is it will pull oxidization from the inside of that tube all the way through to the face of it, and it's going to produce a weld that will likely crack when exposed to high heat, temperature cycles, and vibrations. And that is why, again, if you're screwing around with stainless or any kind of alloy that is sensitive to oxidization and it's thin, which is thin material, let's face it, that's when you're using fusion welding, you want to purge the backside of it with argon so that the weld is not oxided to the point that you're going to have a failure of it. Again, I've repaired a lot of stainless headers that were improperly welded, fusion welded, where the welds crack, and it's due to the lack of an argon purge. Now, on thin tube, if you're not back purging it, or thin material, adding some filler to the side you're welding will likely give you at least some clean material in there, and it will be far less likely to fail than fusion welding. Now, again, fusion welding can be dangerous if you're doing a thin to thick material. The probability of undercut and suckback is almost guaranteed. So again, it's not really desirable to do this except in very specific circumstances, and generally only on the same thickness material. As a bonus nachos, I forgot to mention craterize as a major defect, and this is very significant, more commonly on aluminum than on other things. The picture here depicts aluminum, and what will happen is that crateri will have cracks propagating throughout it due to, again, hot shortness. However, that's not the only defect that can exist in a crateri. It's very common to have what's called a crater pipe, more or less a hole all the way from that crateri through the weld onto the back side. When I started doing Schedule 10 and thinner stainless pipe with fusion welds with TIG, I didn't realize how common it was to have a crater pipe where you'd have a hole that would leak straight through the material. And this is a direct result of tapering off the amperage too fast. Now with pipe welding, where you typically use scratch or lift start and you're not able to slowly decrease the amperage at the end of a weld, you're going to get the crater pipes really bad, especially on thinner material. How you get around this is you more or less keep walking the cup or moving the arc forward, while slowly lengthening the arc gap to where the arc is no longer as focused. It's a way to get around the issue of just snapping out of it really fast and leaving that defect. Now, if you have a foot pedal with your TIG setup, then what you want to do is slowly taper the amperage out and give that crater pipe a time to solidify. And along with pushing more filler at that moment, you will prevent a hole as well as cracking in that crateri. Now, last on the list is what I call hot short cracks, or that's kind of what is going on. And what this is predominantly with aluminum, but it can happen with any number of tool steels and chromoly, all sorts of stuff like that, basically things other than mild steel. And what is going on is if that base material is brought from a solid to molten and then returned to solid fast, it experiences what's known as a hot short crack. The sensitivity of that, the material will be known as hot short sensitive. So aluminum is hot short sensitive. And what that means is you do not want to weld those types of materials where you are fast on the gas of your amperage pedal, your foot pedal with TIG, to where you're hammering on the heat, moving fast, and then just tapering off in an instant. So rather than slowly bringing it up to temperature, letting it stay there as you're welding, and then slowly tapering off, you do everything fast. And what will happen is the base material will often crack. As the weld is solidifying, it will happen almost immediately, or it may have internal defects, which in the case of aluminum, that's very common, especially at craters, where if you taper out too fast with aluminum and you leave a crateri, guaranteed there's going to be cracks already starting there. And where you have cracks, guess what? Propagation of those cracks is very easy. So with hot short sensitive materials, you want to be very careful on how fast you bring the material to being molten, how fast you weld them, and how fast you allow it to solidify. So be very careful. And a good habit, even on mild steel, be a little bit slow to bring everything up to molten with your TIG torch. There's no rush to do it fast. You know, maybe stainless, you can be in a little bit more of a hurry to establish a puddle, but for most things, take your time and then at the end, taper off in a controlled manner. Now, with some materials like, say, thicker aluminum or other kind of tool steels that are very hot short sensitive, on thicker material, oftentimes you're going to end up preheating it. Like on chromoly, thicker than about a 1/4 inch, you want to preheat it, and that is to prevent it from hitting, say, 60, 70, 80 degrees room temperature too fast after welding. And that's something you need to be aware of exists. And with TIG, it's more of a concern because of how fast you can start and stop. And because you're depositing very small high heat input welds with TIG, it's more prevalent with TIG than, say, MIG and stick. I mean, don't get me wrong, if you sat there with your MIG gun and just blasted a bunch of tacks on a hot short sensitive material, you're going to get cracking. But when you're actually doing welds, it's less of a concern with those processes, simply because the heat input for weld size is generally not as excessive, or, well, not really excessive, but not as great as it is with TIG welding. All right, well, let's finish up. So in conclusion, what did we learn today? Well, we learned all about discontinuities and defects with TIG welds. And the truth is that do most of them matter? Yes, absolutely. We as welders or fabricators or just wanting to learn how to weld, we should avoid them at all costs. But guess what? None of us are perfect and defects happen. And that is why it's imperative that you understand what the discontinuity is. Is it a defect? Is it bad enough to where it's going to compromise the structural integrity of what you're welding? AKA, let's face it, if it's an ugly weld full of things that are likely places for cracks to propagate or just has issues, should you go back and grind it out and fix it? Absolutely, yes, you should. Mind your attention to detail. If you're willing to take a little extra time and fix those defects, it will teach you a lot. And guess what? Eventually, you're going to get so sick of fixing those defects that you're probably going to learn to be consistent and smooth and have a proper arc gap with TIG to where you don't have to do it nearly as much. But guess what? The better you are at TIG welding, and it doesn't take that much time to get pretty decent, the less defects and discontinuities you're going to have to fix. So it really pays to practice and have all your mistakes be on test plates and coupons, not stuff you're welding. But hey, when they happen, fix them, not a big deal. TIG is probably the best process to go back and fix defects simply because it's so easy to, and you still have a good looking weld. It's not like with stick where you go back and you're 5 extra passes deep on a 2-pass weld just trying to chase out undercut. Like, you shouldn't have that issue with TIG. With that said, if you got any thoughts, comments, anything to add to this, feel free to. Otherwise, hopefully this video shed some light on some things and maybe helped you fix some of your bad habits moving forward. So with that said, thanks for sticking around. Until next time.